lecture is to talk about cyclohexane conformations, which you can find more reading related to this in 2.5 through 2.6 of your textbook. So as we start to talk about this, I want to remind you of what we're referring to when we talk about cyclohexane and conformations, what the definitions are here. So when we talk about cyclohexane, cyclo means that the atoms are in a ring. And specifically, the atoms that are in the ring are those of hexane. Hex means 6, ane means alkane. So this is a 6-carbon alkane. So we need to build a 6-carbon alkane where the 6 carbon atoms are in a ring. So that's going to look just like a normal hexagon here if we were to draw it out as a line angle formula. So this would be our line angle formula for cyclohexane. The problem with the line angle formula for cyclohexane is that it doesn't give us a clear idea about what the geometry of the molecule is. We have no idea what the three-dimensional shape of this molecule is. And so we need some ways to go about drawing this in a way that more closely represents the three-dimensional structure of the molecule, because certainly in many cases the three-dimensional structure of a compound is what's going to determine what sort of biological functions the compound has. For instance, whether or not a compound is a drug or not is typically related to the exact shape, the exact three-dimensional structure of the molecule. So we need a way to go about illustrating what the three-dimensional shape of cyclohexane is going to be. And when we start to think about the three-dimensional shape, we'll arrive at that by rotating around all of the carbon-carbon single bonds within the molecule. So if we look around the molecule, we have a total of 6 carbon-carbon single bonds connecting those atoms. And we can rotate around those carbon-carbon bonds with some restrictions. The restrictions are imposed because the atoms are locked into a ring. So typically with a alkane that's part of a chain, we can rotate freely around the carbon-carbon bonds to create an infinite number of possible conformations. And we talked in class by drawing Newman projections about the different conformations of linear alkanes, alkanes that are part of a chain. When we start to talk about cyclohexane, where the atoms are locked into a ring, the number of favorable conformations is going to be far more restricted. That is, the number of structures that we expect to see is going to be diminished. There's going to be fewer favorable structures that we can see. The most favorable structure of our cyclohexane is going to be that of a chair conformation. And we call it a chair conformation because if we look at the structure of it, it resembles to some extent a chaise lounge chair. So we're going to bring up here a ball and stick model of a chair conformation of cyclohexane. And as we look at the chair conformation of cyclohexane, the 6 carbon atoms here are shown in black and make up the ring of the molecule. And then the hydrogens that are coming from it, we've highlighted here in red and blue. And if we look at this conformation of cyclohexane, the chair conformation, which is the most favorable conformation, the reason it's favorable is because in the chair conformation, that allows us to have all of the bonds staggered. And if you think back to the terminology related to staggered, when we were discussing the concepts related to linear alkanes and their dihedral angles, we said that the bonds of those linear alkanes were staggered when the dihedral angle was 60 degrees. And the importance of that is that that's going to space the bonds as far apart from one another as possible. Keeping in mind that electrons repel one another, it's advantageous to have those bonds as far away from one another as possible because it's going to increase the stability of the molecule. So we can illustrate the staggering that's occurred here. If we take a look, for example, at this carbon right here, And we look at the bonds that are directly connected to it, coming up to here, and down to there. If I can just get my pen to highlight all three at once, I'd be in good shape. There we go. If we look at the carbon atom that's connected to it on the back side here, which I'll illustrate in pink, so we've got our groups in front there in blue. In the back in pink, I'm going to highlight the three bonds coming from that carbon like so. And if we look at this and we focus, for example, on this bond here at the front, which I'm highlighting in blue, relative to the one behind it in pink, we see that one of those is angled upward, the one in front in blue, and one's angled downward, the one in pink and back. That's the staggering that we see. The dihedral angle, the angle separating those two bonds, would be a 60-degree angle. That's going to be as far apart as we can possibly space the bonds so that we have maximized the distance between all of the different electrons in those covalent bonds within the molecule. So that's going to increase the stability of the molecule by spacing out the electrons. It's also going to increase the stability of the molecule by spacing out the atoms. So in a chair conformation, what the goal is by staggering those bonds, we're going to minimize the torsional strain of the molecule. And when we refer to minimizing the torsional strain, what we're referring to is that we're minimizing the overlap between atoms, or the closeness of atoms, and we're also minimizing the overlap of electron orbitals that are unfavorable. So we're minimizing the torsional strain, meaning we're minimizing the overlap of atoms, because certainly having atoms that are really close together in space is going to make the molecule less stable. So we're minimizing the overlap of atoms, and we're minimizing the overlap of unfavored electron orbitals. So by minimizing those two things, the overlap of atoms and the unfavored overlap of electrons, what we're going to create is the most stable type of conformation of cyclohexane. So it's going to be this general type of structure. And this is a really important general type of structure that we'll see very commonly amongst molecules that are really important biologically. For example, a lot of simple sugars are built on 6-atom rings that certainly adopt this chair conformation. The chair conformation is absolutely essential to the specific properties that those sugars have. So as we talk about the chair conformation of these molecules, rather than drawing out or trying to make a ball and stick model every single time we are working with cyclohexane, we need an abbreviated way to draw a chair conformation. And so the way that we do that will allow us to illustrate the specific structural features of the molecule is if we take this chair conformation, and I'm going to go ahead and erase some of this information here, or try to anyway. So that we can draw underneath this ball and stick model with the way that we're going to go about representing a chair conformation on paper. All right, so to draw chair conformation on paper, we need to keep a few general things in mind. The way that we're going to draw this is by following a general generic template, where we'll draw the template by first creating couple of lines that are parallel here. Like so. And then what I'm going to show in red here is an additional pair of lines that are going to be parallel to one another. So in red, like so, and like so, those are parallel to one another. And then finally, to finish off the hexagon, I'm going to go with purple and go here and here. So you'll notice that the two purple lines are parallel to one another, the two black lines are parallel to one another, and the two red lines are parallel to one another. So what we're going to attach to this ring is we're going to attach groups that point straight up or straight down. We'll refer to those as axial or axial groups if they point up or straight down. And so if we look back at the ball and stick representation, here in red are the atoms that are axial, meaning they point straight up or straight down. So a couple of examples there I'm highlighting. Straight up or straight down means that it's axial. We can show that in our chair conformation that we've drawn down here below by using lines that point straight up or straight down. So as we go around the ring, if we start at either of the top two corners here, you're going to see that those groups are always axial and pointed straight up. As we go around the ring, notice how when we look at the ball and stick model, here our axial group is up. If we come to the next carbon, the axial group is down. If we come to the next carbon, axial group is up. At the next carbon, the axial group is down. At the next carbon, the axial group is up. And finally, the last axial group is pointed down. So the same is going to be true here with our representation that we're drawing. So we start in the up position right here on the upper right-hand side of the structure that we're drawing. Then we come to the next spot and we're going to go axial down. Next one is axial up. Next one is axial down. Next one is axial up. That's the one that we'd already drawn in. And then finally, axial down, which that one's sometimes a little bit hard to show there because it tends to end up being pretty close on paper to the other axial group that was drawn on the other side of the ring there. So in red, what we see are all 6 of the axial groups coming off of the ring. So in the case of cyclohexane, those would all be hydrogen atoms coming off the ring. We will also later on talk about more complex molecules where instead of having just hydrogen branching off of the ring, we have other groups coming off of the ring instead, other assemblies of carbon atoms and things. So red is all our axial groups, and then what I'm going to go in and fill in next are what we'll refer to as the equatorial groups. So in green, we're going to show the equatorial bonds. So the equatorial groups are going to be the ones that are angled slightly up or slightly down. If we look back at our ball and stick model and start back here in the upper right, that bond in green that I'm highlighting that's angled downward is equatorial. If we come to the next atom, our equatorial bond is angled slightly up, next bond slightly down, next one slightly up, next one slightly down, next one slightly up, and that brings us all the way around the ring. So we're going to do the same thing here with our representation that we're drawing of cyclohexane. So we start in the upper right here and we show it angled downward. We come to the next carbon atom and the bond branching off has to be angled upward. We come to the next one, it has to be angled downward. The next one has to be angled upward. Next one must be angled downward. Next one therefore must be angled upward. So you'll see that in order for these to be staggered, as we call it, so that the bond dihedral angles are spread as far apart as possible to maximize the dihedral angles throughout this to 60 degrees, what's going to happen is that we end up with every other equatorial group being oriented downward, upward, downward, upward, downward, upward as we go around the ring. So all of the groups that we just drew in our structure here, that I just circled in black, all of those groups that are in green are going to be equatorial groups. Whatever's bonded to that line there, the line represents the covalent bond, whatever's bonded to that we refer to as an equatorial group. Whatever is oriented straight up or straight down is axial. So to be defined as axial, it absolutely has to be straight up or straight down. Equatorial is all of the bonds that are angled slightly up or slightly down. So what we can do to talk about this a bit more is we can also create a second chair conformation. So we're going to have two possible chair conformations for our molecule that will correspond to rotating around the carbon-carbon bonds of the ring to flip the ring into a second chair conformation. So we're going to draw that second chair conformation here beside the first one that we drew. So this will be an equilibrium process where the bonds are physically rotating. So we'll use an equilibrium arrow to indicate what's going on here. And we'll mention that this is a ring flip. That's the terminology that we use to describe what's happening here. When we say that a ring flip is occurring, what we mean is that the ring is rotating via the carbon-carbon bonds. So what we show in black here, those bonds are rotating. They're restricted in how they are able to rotate because we would like to ultimately maintain a chair conformation in our final ring flipped structure. And so the way that we do that favorably is if we rotate around the carbon-carbon bonds. If you build a molecular model of cyclohexane, which I definitely encourage you to do if you have your molecular model kit handy, if you build a chair conformation of cyclohexane, what you're going to see is that when you do the ring flip, we're going to basically draw our chair structure angled the other way. So you'll see that the structure on the left, the carbon atoms that we've sketched out here in black, are angled opposite the ones on the ring flipped version. So in the ring flipped version, what's going to happen in the ring flip by definition is that when we ring flip, all the axial groups, which I'm going to abbreviate as AX, become equatorial, and all the equatorial groups become axial. We still have a general chair conformation so that we will have the favorable torsional angles. We'll have that angle strain minimized. But all the groups that started off on the left here in red being axial, after we do the ring flip, are going to become equatorial. On the other hand, all the groups that we show in green to start with are going to become oriented straight up or straight down. They're going to become axial. So let's go ahead and draw that into our structure here. So we start off in the structure on the left with the red bonds straight up and straight down as our axial bonds. So once we do the ring flip, once we rotate around the carbon-carbon bonds of that ring, what's going to happen is that by rotating around the bonds of the ring, all those axial groups are going to become equatorial. So I'm going to show in red there, to get things started, our equatorial bond to shown in red there because we flipped from axial on the left to equatorial on the right. On the other hand, the green bonds that started off as equatorial are now axial. They're pointed straight up or straight down. And just like we saw in the structure on the left, it's always going to be the case that the bonds that are axial on those upper two carbon atoms are going to be straight up. So I've just shown in green here the two axial bonds from the carbon atoms in the upper left and upper right. And we can use that as sort of a landmark to help us fill in the rest of the axial bonds. So remember that the axial bonds are going to alternate straight up, straight down, straight up, straight down as we go around the ring, straight up here, straight down here, and that should be our total of 6 axial bonds in this particular molecule. So then I'm going to go ahead and fill in the equatorial bonds. So we did angled down here in the starting point, right here. So we'll do angled up for the next position, angled down for here, angled up for here, angled down for here, and angled up for here. And if you're looking for additional advice on how to draw chair conformations of cyclohexane, if you look at page 86 of the book, there's a nice boxed image there that goes through step by step by step how to go about drawing reasonable chair conformations. This is definitely something that you are going to be expected to be able to do, and they don't have to look perfect, but you definitely need to be able to show me specifically what bonds are axial and equatorial in a way that's very clear. So axial bonds always going to be straight up or straight down. Equatorial bonds are the ones that run around the equator. Those are going to have an angle to them. They're going to be angled straight up. They're going to be angled somewhat up or somewhat down. They're not going to be straight up or straight down. So we have our two major conformations of cyclohexane shown here, the one that we started with and then the ring flipped version. Those are going to represent the two lowest energy conformations that we could possibly make for this cyclohexane by rotating around the carbon-carbon bond. So in the case of cyclohexane, since all of the atoms that are bonded to cyclohexane are all hydrogen atoms, both of these structures would be of identical energy because in both cases they both have all of the bonds staggered, and in both cases all of the atoms, the hydrogen atoms that are coming off the ring, are all equally spaced out in both cases. And we can take another look at this concept of ring flipping and all the axial groups becoming equatorial and equatorial groups becoming axial by taking a quick look at this image, which will hopefully illustrate to you what I was just showing in that previous illustration that I pointed out. So if we look at the location of the atoms within the ring, specifically if we start with carbon number 1 here in the upper right, by definition, when we do the ring flip to give the second possible chair conformation, what's going to happen is that by convention that carbon number 1, when we flip the ring, is going to come down to here. So we're basically moving everything by one spot in the clockwise direction by doing the ring flip. So in addition, the other thing that I want to point out to you that goes back to what we were just drawing out ourselves was that notice how all the axial groups are shown with these green or black atoms attached to the ends of those bonds. When they start out axial, then they ring flip, they all become equatorial. Ring flip situations where we're not just dealing with cyclohexane, meaning all the carbon atoms are directly bonded to other carbons and just the hydrogens coming off the ring as branches, but instead situations where there are groups other than hydrogen that are bonded to the ring coming off as these axial and equatorial groups. So for example, using our template here of a ring flipped chair conformation, where we've rotated around carbon-carbon single bonds of that ring to arise at these two very favorable conformations of cyclohexane. Let's plug on at carbon number 1 here a carbon that's directly bonded to 3 methyl groups. So this carbon is directly bonded to those 3 CH3 groups. So to do a condensed structural formula of that, we can put our first carbon here, which is directly connected to carbon number 1 of that 6 carbon ring that we have numbered 1 through 6 in the ring. And we have our carbon coming off of that ring that's directly bonded to a CH3 group, and we have 3 of those CH3 groups, so we're going to put CH3 in parentheses and then put a subscript 3 next to it. So as we go around the ring, which I'm going to highlight here as well in blue, when we come over to carbon number 4, what I'm going to do is at this equatorial position, I'm just going to throw a chlorine atom on there. And now what I'm going to ask is if we flip the ring, where are those two non-hydrogen branches coming off the ring going to end up? So we started at carbon number 1 with our CCH3 group being axial. I'm just going to put an AX there. And our chlorine atom was equatorial. So after we ring flip, remember that we said by definition when we ring flip, all the axial groups become equatorial and all the equatorial groups become axial. So when we do this ring flip, we need to keep in mind that our group that started off as axial here in the upper right corner, that CCH3 group, is going to become equatorial. On the other hand, the chlorine atom that's equatorial to start with is going to become axial. And by convention, when we redraw the ring after the flip, we take each of the atoms of the ring and basically move them one spot clockwise. So atom number 1 of the ring, this carbon atom right here, once we do the ring flip, I'm using that arrow to show that we have moved that carbon number 1 down to here. So I'm going to circle that right here. And that's the way to think of it when we're doing the ring flip. So at carbon number 1 here, that's the carbon atom that has the CH3 group bonded to it. So in the ring flip version, remember that all the axial groups have become equatorial. So rather than that CCH3 group being oriented straight up or straight down, instead it needs to be angled slightly upward in this case. So we'll put our CH3 here. So axial has now become equatorial. And we did that by rotating around the carbon-carbon bonds within the ring. And if we look at the chlorine atom at carbon number 4, and we move around the ring to carbon number 4, keeping in mind that we are basically taking each of the spots and going one spot clockwise, that would put carbon number 4, instead of being here at the front left, instead it's going to be back here at the back left. And the chlorine group that was directly bonded there at carbon number 4, that was equatorial, is now going to be axial, because by definition when we do that ring flip, we're always switching all the axial groups to equatorial and all the equatorial groups to axial. So now our chlorine atom is axial. As we look at these two structures, what we're going to find is that the two structures are not going to be equivalent in energy. One of them is going to be lower in energy than the other. And what's going to give the lowest energy here is that the lowest energy is going to always correspond to a situation where we have the bulkiest groups in the equatorial position. So our lowest energy is going to occur if the bulkiest group is equatorial, because the equatorial positions are going to allow the atoms to be spaced out more in space relative to being axial. So if we look at the groups that are coming off of the ring in our example problem here, our CCH3 group is going to be quite bulky. If we were to build a molecular model of that, we'd see that it would take up definitely a lot of space relative to a chlorine atom or relative to a hydrogen atom. So that's our bulkiest group. And so the energy is going to be lowered if the bulky group is equatorial, because it's going to run into less strain, less stress with the other atoms. So if it's in this axial position, what's going to happen is that the bulky group is going to end up very close in space to the other axial atoms that are oriented up. So we would envision that this CCH3 that we've circled in green here in the structure on the left is going to be really close in space to the other axial up atoms, which I'll circle here in green and green. So those three green circled atoms, or green circled groups, are going to be very close in space in the axial conformation. On the other hand, if we do a ring flip, our CCH3 group now is instead equatorial. And equatorial groups spacing out around the equator of the molecule are going to be inherently more spread apart from the other atoms, and therefore that is going to be lower in energy because the atoms are less closely compacted together. That strain of them being close together, or steric strain as we call it, is going to cause the structure on the left here to be higher in energy than the structure on the right. So looking at these, we can label the guy on the left as the higher energy one. Meaning that it's less stable. Whenever we say something is high energy, what we're referring to is it being less stable. And the one on the right is going to be lower energy. And the reason it's lower energy is because of the fact that that bulkiest group there, our CCH33, is equatorial rather than axial. Equatorial reduces the steric hindrance within the molecule. So the bulkiest group being equatorial is going to lead to lower steric hindrance. When we say steric hindrance, what we're referring to is atomic crowding. The molecule is more stable if the atoms are spread as far apart as possible. So we were just looking at the ring-flipped versions of a molecule that had a carbon bonded to 3 methyl groups, and then a chlorine over here at carbon number 4 of the ring. So I've drawn sort of a simplified representation of that where I haven't shown every single bond coming off the ring. Instead, only I've shown those bonds that have non-hydrogen group attached, and that's a perfectly acceptable way to do this. So if we do the ring flip with that, basically going back to what we had drawn on the board here a little bit earlier, if we ring flip that, we bring our group from carbon number 1 down 1 spot to right here, and we plug that group on. It was axial, now it's become equatorial because we did the ring flip, rotating around those bonds. The chlorine atom started off equatorial, so now it needs to still be at position number 4 of the ring, but it needs to be axial. So we're going to plug that in as an axial chlorine. And there's another way that we can describe these groups relative to one another. Instead of just saying that the carbon bonded to the 3 methyl groups is equatorial and the chlorine is axial, instead, we can say how those groups are appearing on the molecule relative to one another by describing them as cis or trans. And what we mean when we say that two groups are cis to one another is we mean that those two groups are both on the same face of the molecule. If they're trans, on the other hand, they are on opposite faces of the molecule. And what we mean when we say that they are on the same face of the molecule, that means that both of the lines leading to those atoms are oriented upward relative to the carbon atom that they're bonded to, or that they're both oriented downward relative to the carbon atom that they are bonded to. In other cases, if they're trans, what's going to be the case is that one of the groups is oriented upward and the other is oriented downward. So let's look at the molecule up here as an example. So the chlorine bond going to that atom, we would say is oriented upward. Keep in mind, upward is not synonymous with axial. It just means relative to the carbon atom that we're bonded to. Does that line go upward relative to that or downward? So this one goes upward. So we would say that that chlorine atom is on the top face of the molecule. If we come over to this carbon atom, it definitely is oriented upward. So we would say it is also on the top face of the molecule. Thus, both of those groups are on the top face of the molecule, meaning they're both on the same face. So we would say that those two groups are cis to one another. If we come over to the ring-flipped version, where we've rotated around carbon-carbon bonds to create this second conformation, we can look at the chlorine atom, and what we see is that it is oriented upward relative to the carbon that it's bonded to. I'm showing that bond in red. Likewise, we come over here to our carbon atom, And we see that that bond is oriented upward as well. So since both of those are oriented upward relative to the carbon they're bonded to, it's still cis. So this brings us to one key point, and that is ring flips will not change whether two groups are cis or trans to one another. So ring flips never, very rarely do we say never, ring flips never change the cis and trans relationship of two groups relative to one another. The only way to change that is to actually do a chemical reaction where you would physically be completely breaking apart the two atoms and then rejoining them differently. So by just rotating around carbon-carbon bonds, which is what we're doing in a ring flip, you're never going to change cis to trans or trans to cis. That relationship is always going to stay the same. So we could draw different structures for different molecules that would represent the trans molecule that has a carbon with 3 methyl groups bonded at carbon number 1 and then at carbon number 4 chlorine. So the way that we would do that to show these as trans to one another is I draw my cyclohexane again, and at carbon number 1 I'm just going to put in my carbon bonded to the 3 methyl groups. Doesn't matter if it's axial or equatorial. What matters is how the chlorine atom is going to be showing up relative to that. So we show our carbon atom here coming off the ring with that black bond upward. So if we're going to be making a trans molecule, meaning we want the two groups on opposite faces of the molecule, then when we come over to carbon number 4, since we said that was where the chlorine atom was, that chlorine had better darn well be pointed downward, like so. That's going to indicate that the two are trans because the position number 1 bond is oriented upward. It's on the top face of the molecule. On the other hand, the bond that we're focusing on at carbon number 4 is oriented downward. It's on the bottom face of the molecule. We can do a ring flip of this to give the other possible chair conformation for the trans molecule. So we do that ring flip. Following our convention, we're going to create a chair that's oriented in the other direction, like so. And also by convention, we're going to take that number 1 position, which was in the upper right-hand corner. It's going to move to the lower right corner. Then we just go around clockwise, numbering our atoms from there. And at position number 1, after the ring flip, that group that was axial had now become equatorial. So we'll go ahead and show that. At position number 4, we start off axial. So now, once we've done the ring flip, I'm going to create a little more room for myself here by drawing that arrow smaller. We have that chlorine group is equatorial. So in ring flipping, all the axial groups became equatorial, all the equatorial groups became axial, and if we've done this right, trans should stay trans. So that's definitely the case here because if we look at the bond of the chlorine, it's oriented downward relative to the carbon atom. Bond to the carbon off the ring is oriented upward. So that means that those two groups are still trans to one another. That's always going to be the case when you do a ring flip. Trans will stay trans. So as you might have noticed, it's a little bit cumbersome to draw these chair conformations over and over again. And if you're just trying to simply illustrate that two groups are cis to one another or trans to one another, you might want to do it in a way that's a little bit quicker than drawing out the chair template every single time. So as a result of the need to be able to draw these relatively quickly, there is a shorthand way to simply represent whether two groups are cis to one another or trans to one another. It doesn't tell whether the groups are axial or equatorial, but it will tell you whether those are cis or trans to one another. You go about creating an abbreviated way of showing whether two groups are cis or trans to one another. So we're going to look at line angle formulas that will show us whether two groups are related to one another, cis or trans. It's a very important thing to do because what is often the case is that the properties, particularly how molecules interact with biological systems, is going to differ depending upon whether those molecules are cis or trans. For example, lots and lots of drug molecules act by inhibiting enzymes, and it's very common that the cis molecule will inhibit an enzyme, whereas the trans one will not, or vice versa. So what seems like perhaps a minor structural change, the orientation of those atoms, can lead to a very significant effect on the biological function of a molecule. So if we want to quickly show whether two atoms are cis or trans to one another, the way that we can do is we make our hexane ring here in our line angle formula, and then if the two groups are cis to one another, the way that we show that is by using two wedges going to those, and I've just drawn those wedges in red. That indicates that the bond is coming toward you. It's pointed out of the page and toward you. And so if we want to draw that carbon bonded to the three methyl groups here, we can draw our fingers coming from that. And what we will do is, looking at that and then coming over to position 4, we have our chlorine. Notice how both of the bonds are oriented toward you. They're both wedges. That indicates to us that those two groups are cis to one another. Cis means same. It means they're both pointed in the same direction. They're both on the same face of the molecule, both pointed upward. Another way that we could just as effectively go about showing that those two groups are cis to one another is by showing both of the groups using dashes. So the dash is what I'm just showing here. And that indicates also that the groups are pointed in the same direction. It just indicates they're both pointed away from us instead of both pointed toward us. So these are both perfectly acceptable ways to go about drawing cis molecules. So this would represent a molecule that has groups bonded at carbon 1 and carbon 4 of the ring and that are cis to one another. Likewise, we can do something similar here for trans molecules. And with trans molecules, what's always going to be the case is that one of the groups is pointed toward us and the other one is pointed away from us. So for example, this would be a trans representation of this molecule. Notice how one of the groups is a dash going off of the ring, the other is a wedge. So one of those bonds is coming toward you as a wedge, the other is pointed away from you as a dash. That's going to mean that those two are trans, they're opposites, on opposite faces of the molecule. Another way that we could go about representing that would be just fine as well, is that we could show the bond going to the carbon atom coming off the ring as a wedge, and the bond to chlorine, we could show the bond coming off of the ring as a dash, and we could also show the bond to the chlorine as a dash. Both of those are pointed away from you, so that would actually be cis. So we need one of those pointed toward us, one pointed away from us to get this trans. So that one's pointed toward us, the one on the chlorine is pointed away from us. So now those two are opposite, and that would definitely be trans. So these two are the trans ways of drawing this molecule. Notice how one of the groups is pointed toward us as a wedge, the other is pointed away from us as a dash, and we just switched which one was which here and going from one structure to the other, but they're certainly both trans. This doesn't tell us anything about which groups are axial, which groups are equatorial specifically. You would have to use a chair conformation for that, but this is a quick and dirty way of illustrating whether the groups are cis or trans to one another.